another example up here. This one I'll tell you is going to be somewhat similar to what we did last time. We're going to do this with a u substitution, but after we do the u sub, we're going to have an extra piece that we need to rewrite in terms of u. So I'm going to suggest that you pause the video and try to work this out on your own. Once you've done that, check back in. Welcome back. So I do see here that I have two different function compositions. This is secant plugged into the fourth power function, and this is 1 plus tan x plugged into the square root function. Now, you might have a sense of which one you think is going to work, but if not, just write them both out. If I tried u equals secant of x versus u equals 1 plus tangent of x, well here u prime would be secant of x times tangent of x. And I can see that's just not going to work, because while I could say this is 4 copies of secant, so that's 3 plus 1 that I need to set aside for the du, I don't have a tan x, because that's not just a tan x, that's tan x being added to 1 under the radical. So that doesn't look too promising. But here u prime would be secant squared x, because of course the derivative of 1 is just 0, and I do have that. Okay, so du would be secant squared x dx. So let's try breaking this apart as secant squared x times secant squared x times root 1 plus tan x dx. Now with this u sub, I can say that and that are going to become my du. This is going to become the square root of u, or u to the 1/2. But I've got this extra piece right here. What does that become? So I've got a secant squared x. Well, when I've got an extra trig function, kind of happy when it's an even power. Because if it's an even power, I've got my Pythagorean identities. Now, you may or may not have all 3 versions of the Pythagorean identity memorized. I don't care whether you do. I want you to know that they exist. Okay? So you should know the main one, which is sine squared plus cosine squared equals 1. And then you should remember that tangent and secant have something really important in common. They both have a cosine in the denominator. So if I want to get to the version of the Pythagorean identity that has tangents and cosines in it, I just divide through by cosine squared. So that's going to give me tangent squared x plus 1 equals secant squared x. Nice. Okay. So if I've got a secant squared x, tangent of x here was u minus 1. So that's u minus 1 squared plus 1 is equal to secant squared x. Okay, so u minus 1 squared plus 1, and all of that is still getting multiplied by that u to the 1/2. So I can write that extra piece in terms of my u substitution. Now that I have that, let's take a look, because I still have a fairly complicated integrand here, but I just see a bunch of arithmetic that I can do because everything is in terms of a power of u, or at least it will be once I multiply this out. So that's the integral of that would become u squared minus 2u plus 1. So right now it's a power of u minus 1, but when I multiply it out, all powers of u, plus 1, and then times u to the 1/2 du. Okay, so I'm going to just combine those to get a 2, and then let's distribute that u to the 1/2. So with multiplication and division, we want to remember we don't have a nice rule, unless somehow we're able to rewrite the multiplication doing a u sub. But if I've got multiplication in my integrand that I'm not able to deal with it with a u sub, I got to do the multiplication. Okay. So let's see. This is going to be u to the 5/2 minus 2u to the 3/2 plus 2 u to the 1/2 du. Okay, so I can integrate. So now I'm going to get u to the 7/2 dividing by that power is going to be 2/7 minus 2 times u to the 5/2 dividing by that power is times 2/5 plus 2 times u to the 3/2 dividing by that power is times 2/3 plus a c. So all I'm going to do now is multiply out the coefficients and substitute back in what u was. Remember, u was 1 plus tan x. So we're going to get 2/7, 1 plus tan x to the 7/2 minus 4/5, 1 plus tan x to the 5/2 plus 4/3, 1 plus tan x to the 3/2 plus c. All right, and so there's our integral. Excellent.